The flaw was always there. There is a moment just before something changes permanently, where everything still looks the same, the equipment is the same, the equations are the same. The men working late in their offices are the same men they were the week before, drinking the same bad coffee, writing in the same notebooks with the same slightly cramped handwriting that comes from years of fitting large ideas into small margins, and then one of them writes a number. Not a discovery, not a revelation, a number, a fudge, he will call it later. A trick to make the math behave. He writes it down and goes home, and the universe does not shake. The coffee does not get better. Nothing announces itself. And yet, the year is 1900. Max Planck is trying to solve a problem that sounds from a distance like it should be a small one. Hot things glow. You already know this. A piece of iron heated slowly goes from dark to red to orange to a kind of white that hurts to look at. A fire has colour. A star has colour. Even the coils of an old electric stove, if you turn it up high enough, will go faintly red in the dark. The colour of a hot thing is connected to its temperature, and by 1900 physicists had been staring at this connection long enough to expect that the mathematics would eventually just yield, that someone would find the right shape for the equation, and the thing would close. It did not close. What they had instead was two equations. One worked at low frequencies of light. One worked at high frequencies. Neither worked across the whole range. And when you took the equation that handled the high-frequency end and pushed it toward the low end, it did not gently fail. It went to infinity. It predicted that a hot object should pour out infinite energy at short wavelengths, which is a way of saying it predicted something the universe has never once done in the entire time the universe has existed. Physicists called this the ultraviolet catastrophe, which is one of the better names physics ever came up with for anything, even though catastrophe is too large a word for what it actually was. It was not a catastrophe. It was a door that would not open. Planck was not young when he sat with this problem. He was 42. He had been a physicist long enough to have strong feelings about how physics was supposed to work, and one of his strongest feelings was that nature was continuous, that between any two temperatures, or any two frequencies, or any two states of any physical thing, there were always more states in between. You could always find a smaller step. The world did not jump. The world flowed. He believed this the way people believe things that have always been true in their experience, not as a choice, as a background condition. What he found, working backward from the data, was that the only equation that fit, the only one that described what hot objects actually did across all frequencies, not just some of them, required something that should not have been there. It required the energy to come in chunks, not a flow, not a continuum. Discrete packets, each one a fixed size, the size depending on the frequency of the light. You could have 1 packet, or 2 packets, or 17 packets, but you could not have 1.5. The in-between did not exist. The floor, which Planck had always assumed was smooth, turned out to have a grain. He called these packets quanta, from the Latin word for how much, the constant that set the size of each packet, the smallest possible ratio between a packet's energy and its frequency. He called h. We still call it h. We call it Planck's constant, and it is one of the fixed numbers of the universe, the kind that shows up everywhere once you know to look for it, the kind that does not change regardless of where you are or when you are or what you are measuring. Its value is approximately 6.626 times 10 to the negative 34th joule seconds, which is an almost comically small number, the kind of number that makes you feel the ground is further down than you thought. He wrote it in. The equation fit. He went home. He did not think it was real. This is worth pausing on because it is strange. Not metaphorically strange. Actually strange in the way that a person's behavior can be strange when they are doing something they do not understand. Planck had found the correct description of how energy behaves at small scales. The description worked. The predictions matched the measurements with a precision that should have felt, at minimum, like something. But his interpretation was that he had performed a mathematical convenience, nothing more, a trick to make the integral converge. He assumed that when someone smarter came along, or when the right framework appeared, the chunks would dissolve back into a continuum and the world would return to flowing the way he had always known it to flow. He spent years trying to make this happen. He tried to find a version of the same result that did not require discreteness. He could not find one. And not because he was not looking hard enough. He was one of the most careful mathematical physicists of his generation, but because the discreteness was not a scaffolding holding up a deeper result. It was the result. The chunks were not a placeholder for something smoother. They were what was actually there. It took him a long time to accept this. Some historians of physics think he never fully accepted it. Not in the way that later physicists accepted it. He had grown up in a physics that was built on certain assumptions about the nature of continuity, and those assumptions were not wrong exactly. They were just not deep enough. They described the world at the scale where humans live and measure and touch things. At a smaller scale, something else was going on, and it had been going on the whole time underneath everything without anyone knowing. The flaw was always there. They had just never needed to look at it before. Here is a question worth sitting with. If Planck had believed his own result from the beginning, would physics have moved faster? Or does the hesitation matter? Does the fact that he held it at arm's length for years give the rest of the field time to catch up to something that would have been, if dropped all at once, too strange to absorb? There is no answer to this. It is just something to wonder about. What happened next did not come from Planck. It came from a 26-year-old patent clerk in Bern, Switzerland, who in a single year, 1905, which physicists sometimes call the miracle year, though miracle is probably too soft a word for what it was, published 4 papers, any one of which would have been enough to secure a reputation. One of those papers was about Brownian motion. One was about special relativity. One introduced the equivalence of mass and energy. The paper that eventually became E equals mc squared, which is the most recognized equation in the world, and also one of the most misunderstood. And one was about light. Specifically, it was about what happens when light hits metal. The photoelectric effect had been observed before Einstein wrote about it. Heinrich Hertz noticed it in 1887, more or less by accident, while he was doing experiments with electromagnetic waves. When ultraviolet light hit certain metal surfaces, electrons came off. This was the observation. It was noted, filed, occasionally puzzled over, and not resolved, because the behavior of those electrons was wrong in a way that nobody had a framework for yet. Here is what was wrong. If you took classical wave theory, the physics that described light as a wave, which it behaved like in every experiment anyone had done up to that point, and used it to predict what should happen when light hits metal, you would predict that the energy of the electrons coming off should depend on the intensity of the light. Brighter light means more energy in the wave, means electrons get knocked off with more energy. This is the intuitive prediction. It feels correct. Waves carry energy spread across their whole surface, and a bigger wave carries more. But that is not what happened. The energy of the electrons did not depend on the intensity of the light at all. It depended on the frequency. Low-frequency light, no matter how bright, produced low-energy electrons, or no electrons at all, if the frequency was below a certain threshold. High-frequency light, even very dim, produced high-energy electrons. And below the threshold frequency, nothing happened regardless of how long you waited or how much light you used. There was no delay during which energy slowly accumulated. Either the frequency was high enough and electrons came off immediately, or it was not high enough and nothing happened. Ever. This made no sense if light was a wave. Einstein proposed that it made perfect sense if light was not, in fact, a wave. Or not only a wave, if light came in packets, if Planck's quanta were not just a mathematical trick but were actually what light was made of, if each packet carried an energy proportional to its frequency, and that energy was delivered all at once to a single electron rather than spread across a surface, then everything about the photoelectric effect fell into place. Low-frequency packets do not carry enough energy to free an electron from the metal. High-frequency packets do. Intensity just means more packets, not more energy per packet, so it affects how many electrons come off, but not how energetic those electrons are. It was a clean solution, almost too clean. It also meant that light was made of particles, which was a problem, because light was made of waves. Everyone knew this. Thomas Young had demonstrated it in 1801 with his famous double-slit experiment, sending light through two narrow slits and watching the interference pattern appear on the screen behind them. Waves interfere. That is what makes them waves. They add where they overlap in the same direction and cancel where they overlap in opposite directions, and the result is a pattern of bright and dark bands that has no particle-based explanation. A particle goes through one slit or the other. A particle does not interfere with itself. The interference pattern is not a thing a stream of particles produces, and yet the interference pattern was real, and the photoelectric effect was real, and both were light. This is the place where quantum mechanics begins, really. Not with Planck's equation, which was a fix for a technical problem, not with Einstein's Nobel-winning paper, which proposed an explanation, but with this. Two experiments, both correct, both describing the same thing, pointing in directions that had no business both being right. One said particle, one said wave. Both said yes. There is something I want to linger on here, because it does not get enough room in most accounts. The people working through this in the early 1900s were not confused in the way that a student is confused when they have not yet understood something. They understood everything there was to understand with the tools they had. The confusion was not a gap in their knowledge. It was a property of the thing they were looking at. Light was not behaving confusingly because physicists had missed something. It was behaving confusingly because it was, in some fundamental way, a confusing thing. A thing that did not fit into the categories that had been built to describe things. Particle and wave are human categories. They are shapes of thought that grew out of experience at a scale where particles are particles and waves are waves, and the two never overlap. At the scale of light, at the scale of electrons, the categories did not hold. The world did not fit in them. And the question was not, could you find a better fit? Could you find a smarter category that contained both? But whether the insistence on fitting was itself the problem. That question would take decades to fully come into focus. In 1905, most people working in physics were still trying to find the better category. The idea that there might not be one, that you might have to build an entirely new way of thinking about what a physical thing is, was still some years away. Planck's constant went quietly into the equations and stayed there. The equations kept working. Spectral lines of hydrogen, the precise frequencies at which hydrogen absorbs and emits light. Those had been measured carefully for decades, and nobody knew why hydrogen only ever used those specific frequencies, why there were gaps between them, why the pattern was what it was. Niels Bohr in 1913 used Planck's constant to build a model of the hydrogen atom in which electrons could only occupy certain orbits with specific energies and could only jump between them by absorbing or emitting a photon of exactly the right energy. The model was not right. The picture of an electron orbiting a nucleus like a planet turned out to be approximately right in the way that a hand-drawn map is approximately right, capturing the general shape of things while missing what the place actually looks like. But the spectral lines it predicted matched the measurements so precisely that it was hard to dismiss. Something was being constrained. Something inside atoms was not allowed to take any value it wanted. It was allowed certain values and not others, and the gap between the allowed values was not an accident, but a mathematical fact, connected to Planck's constant, showing up now in a new place as if it had been there all along, waiting for someone to draw the right lines. What does it feel like to be in a field that is suddenly full of a number that nobody put there? You notice it. You use it. You do not necessarily understand it. Understanding comes later, if it comes at all. For now it is a feature of the landscape, the way a mountain is a feature of a landscape. You navigate around it, you use it as a reference point. You do not question why it is there because it was there before you arrived, and it will be there after you leave. By 1920, the situation had become, depending on who you were, either thrilling or deeply uncomfortable. Thrilling because the quantum picture was working. Wherever you pressed it, it pressed back correctly. The predictions were holding. The spectral lines, the photoelectric effect, the behavior of electrons in atoms, all of it obeyed rules that classical physics did not contain, and the new rules were strange, but they were consistent. And consistency in a theory is a kind of beauty, even when the theory itself is hard to look at. Uncomfortable because nobody knew what the theory meant. There is a difference between a theory that works and a theory that makes sense. Classical mechanics worked and made sense. You could draw a picture of a billiard ball and trace its path, and the picture meant something. It corresponded to what the ball was actually doing at each moment in time. The quantum picture worked, but the picture, when you tried to draw it, did something funny. It either went wrong or it went nowhere. The electron in Bohr's model occupied a circular orbit, but the moment you asked what the electron was doing between measurements, the orbit went quiet. The model had nothing to say about between. It only worked at the moments when something happened, and between those moments there was just nothing, or not nothing. The question did not have an answer in the language the model spoke. This is the grain that Planck found in 1900, and it goes deeper than it looks. It is not that the theory was incomplete, it is that the question, what is the electron doing right now at this moment when nobody is measuring it, might not be the kind of question that has an answer. That possibility would take another decade to fully surface. For now, in 1920, people were still mostly trying to improve the picture, still trying to draw the orbit more precisely, still assuming that the between existed and was just waiting for a better model to describe it. They were still, without knowing it, standing on the floor, not yet ready to look down. What I keep coming back to, thinking about this period, is how long things took to settle. Not because people were slow, because the thing was genuinely hard, because you cannot accelerate the process of recognizing that your basic categories are wrong. The categories do not feel like categories from the inside. They feel like the shape of reality. When you have spent your whole intellectual life understanding that particles have positions and velocities, and that you can, in principle, know both at once, the suggestion that this might not be true does not arrive as an interesting idea. It arrives as a mistake, as something to correct, as the sort of thing a careful reading will resolve. The careful readings did not resolve it. They made it stranger. Planck wrote his number and went home. The number was real, and the thing the number was pointing at, the thing underneath the floor, had been there all along, doing what it does, indifferent to whether anyone was ready to look at it. It is still there. It is doing it right now. There is a question I want to leave with you as this chapter ends, not because there is an answer, but because it is worth carrying forward. At what point does a convenience become a discovery? Planck called his constant a trick, a fix, a way to make the integral work. He did not believe it was real, and he was wrong about that, but in a way that is hard to be too harsh about, because the thing he found was so far outside what physics said was possible that disbelief was almost the only reasonable response. How many times has that happened? How many times has someone written a number to make the math work, filed it away as a placeholder and been wrong about what they were holding? How would you know? The flaw was always there. The question is only ever whether you are ready to feel it. Everything we thought was smooth. Continuity is one of those ideas that felt so obviously true that it never really needed defending. Between any two notes on a piano there is a pitch. Between any two temperatures there is a temperature. Between any two positions of a moving object there is a position, and between that position and the next one there is another position, and the chain of positions never breaks because the object is always somewhere, and somewhere is always one of infinitely many points along a continuous line. This is not a physical theory. It is closer to a feeling about how space works, about what it means for something to exist in space at all. The feeling was so deeply embedded in classical physics that it rarely came up as an assumption. It was more like the air the assumptions breathed. And then it turned out to be wrong, not completely wrong, not wrong at the scale you live and move and measure things with your hands, but wrong in a specific direction, at a specific depth, in a way that could not be patched or softened or explained away as an approximation. The word discrete is the opposite of continuous, and it is the word that quantum mechanics handed to physics like a note passed under a door. Discrete means separate, distinct, countable. It means there is a gap between the allowed values, and the gap is not small. Not so small that it becomes continuous again if you look closely enough, but real, fixed, permanent. An electron in an atom does not get to have just any energy. It gets to have certain energies. The ones in between are not available. Not approximately available, not available under slightly different conditions, just not available. The spaces between allowed energy levels are not like the spaces between steps on a staircase, which you could in principle fill by building smaller steps. They are more like the spaces between integers. You cannot fill them by being more precise. 3 is not closer to 4 if you look at it more carefully. It is just 3. This was the grain Planck found in 1900, and what happened in the 2 decades that followed was that the grain showed up everywhere. Not because physicists were looking for it everywhere, because it kept being there. Niels Bohr in 1913 built his model of the hydrogen atom on the idea that electrons could only exist in certain orbits, each orbit corresponding to a specific energy, each jump between orbits producing or absorbing a specific parcel of light. The model was a hybrid. It used classical physics where it could and pasted the quantum condition on top where it had to. And Bohr was not entirely comfortable with his own construction. He knew it was a scaffolding, not a building. But the spectral lines it predicted were correct to a precision that could not be coincidence, and so the scaffolding stayed up while people tried to figure out what the building underneath it actually was. What was strange about Bohr's model, stranger even than the discrete orbits, was what it did not say. It did not say anything about what the electron was doing between the orbits. When an electron jumped from a higher energy level to a lower one, emitting a photon in the process, the model had nothing to offer about the transition itself. Not a description of a slow movement from one orbit to the other, not a path. The electron was in one state, and then it was in another state, and the interval between those two things was simply not in the model. The jump was instantaneous in the sense that the model had no language for the during. Not that it happened quickly, that the during was not a thing the model contained. Bohr did not dwell on this in his 1913 papers. He probably should have. The absence of a description of the during is not a minor gap. It is the gap, the place where the weirdness lives. He had found a way to describe what happened at the before and the after, and the between was a wall, and he walked quietly past the wall, and the model worked well enough that nobody made him go back and explain it. Meanwhile, the smooth world was giving way in another direction too. Einstein in 1905 had proposed that light came in packets, photons, each with an energy proportional to its frequency. The photoelectric effect confirmed this. But light had also been showing interference patterns since Young's experiment in 1801, and interference is something waves do, not something particles do. So light was packets, and light was waves. Both, at the same time, depending on how you asked the question. This bothered people. It bothered people in a sustained, low-grade, professional way that did not go away no matter how many careful thinkers spent careful time on it. In 1924, a French physicist named Louis de Broglie, in his doctoral thesis, proposed something that his committee apparently was not sure whether to pass or not. They wrote to Einstein, who said it was fine, And so it was passed. And the proposal was this: if waves can behave like particles, perhaps particles can behave like waves, not as a metaphor, as a physical claim. A moving electron should have a wavelength. The wavelength should be inversely proportional to its momentum, connected by, of course, Planck's constant. An electron is a wave the way light is a wave, not continuously, not always, not in the way that water is a wave, but in the way that something can be two things depending on what the experimental setup requires of it. This was tested 3 years later, in 1927, when Clinton Davison and Lester Germer in the United States, and separately George Thomson in Britain, fired electrons at crystal surfaces and watched them produce diffraction patterns. Diffraction patterns. The thing waves make when they bend around obstacles or through gaps. Electrons, going through a gap or bouncing off a crystal lattice, spread out the way waves spread out, interfere with themselves the way waves interfere with themselves, and land on a detector in a pattern that has no business being there if electrons are particles. They are particles. The interference pattern is still there. The smooth world does not go quietly. There is something in human reasoning, not a flaw exactly, but a tendency, that wants to save the continuous picture. That wants to say, yes, but surely there is a deeper level at which things are smooth again. Surely the discreteness is a surface feature of something that, underneath, flows. Surely if we go far enough down we will find the continuum waiting. Quantum mechanics, as it developed through the 1920s, kept refusing this. The discrete energy levels were not approximations of something continuous. The wave-particle behavior of light and matter was not a sign that the real thing underneath was one or the other. The gap between allowed states was not a gap in knowledge. It was a gap in nature. And the mathematics that described it, which Werner Heisenberg developed in 1925 in the form of matrix mechanics, and which Erwin Schrödinger developed independently in 1926 in the form of wave mechanics, and which Paul Dirac and others then showed were actually the same theory written in different notations. That mathematics was not a placeholder for a deeper continuous description. It was the description. The grain went all the way down. What does it feel like to live in a world where the floor has texture at a scale you cannot feel? Mostly nothing. The grain is so fine, Planck's constant so small, that for any object you can touch or see or move, the discreteness is completely invisible. The steps in the energy levels of a hydrogen atom are tiny compared to the thermal energy bouncing around at room temperature. The wavelength of a baseball in flight is so short it cannot interact with anything at the scale of a baseball. The quantum world is far below the threshold of ordinary experience, and so ordinary experience feels continuous, feels smooth, feels like the picture it has always been. The continuity you experience is real, in the sense that it is what happens at your scale, but it is not fundamental, it is emergent, a consequence of the fact that you're very large compared to the grain, and so the grain averages out, the way the graininess of a photograph averages out when you hold it at arm's length. Step closer, the grain appears. Step closer still, and the photograph stops being a photograph and becomes just dots, and the smoothness you saw from a distance was never actually there. This is the thing that takes a long time to settle. Not understanding it, feeling it. The world you experience is a high-altitude view of something that is not smooth. The smoothness is real to you. It is not real to the world. There is a question hiding in all of this that the physics of this era did not ask directly, but that the mathematics kept implying. If energy comes in chunks, and electrons live in discrete states, and matter has wavelengths, then what exactly is the thing that has these properties? What is an electron? Not in the sense of what does it do. That was increasingly well described. But what is it? What kind of thing goes through a crystal and makes an interference pattern? What kind of thing lives in discrete energy levels and jumps between them without a during? The answer that eventually came was not an answer in the usual sense. It was more like a description of why that question was harder than it looked. But that comes later. In the 1920s, the question was still being asked in the old way, with the old confidence that asking carefully enough would eventually produce a clear picture. The picture did not come. Something else came instead. What the light did that it was not supposed to do. Think about the last time you were in a room when someone turned on a light. Not a gradual thing, not a dimmer easing up, but a switch. The kind that goes from nothing to everything between one moment and the next. The room is dark, and then the room is lit, and your eyes take a moment to catch up, to adjust, to decide what they are looking at. In that small moment of adjustment, there is something almost biological happening. A rush of signals along pathways that have been doing this since before your species had a word for light or a concept of a room. The photons hit the retina, the chemistry responds, the signal goes. None of that is what we are going to talk about, but hold it for a moment. That ordinary rush. Because the ordinary rush is built on something that physicists in 1905 were just beginning to realize they did not understand. The photoelectric effect looks, on paper, like a narrow technical problem. Light hits metal, electrons come off. Adjust the numbers, write the equation, move on. It sounds like a problem with a solution, and in one sense it had one. Einstein wrote the solution in March 1905. In a paper whose title translates roughly as On a Heuristic Point of View Concerning the Production and Transformation of Light, which is a careful hedged title for a paper that was quietly going to change everything. Heuristic. He used the word heuristic, meaning useful, meaning a working assumption rather than a proven truth. He was not claiming to have proven that light was made of particles. He was claiming that if you assumed it was, the photoelectric effect became easy to explain. It became easy because the wrongness of the photoelectric effect, the specific way it failed to obey the rules, was exactly the wrongness you would predict if light came in packets. Here is the wrongness, laid out slowly, the way it deserves to be. Classical wave physics predicted that the energy given to an electron by light should depend on the intensity of the light. More light, more energy delivered to the surface, more energetic electrons. This is intuitive. It is the behavior you would expect from any wave delivering energy to a surface. Ocean waves hit a beach and pile up. A bigger wave does more. A louder sound moves a diaphragm more. Energy and intensity go together. This is so basic an expectation that it almost does not need to be stated. But the electrons came off with energies that had nothing to do with the intensity. Nothing. You could make the light 10 times brighter, and the electrons would come off exactly as energetic as before. There would just be more of them. The energy per electron was locked, immovable. The only thing that changed it was the frequency of the light, not the amount of light. And below a certain frequency, a specific threshold, different for different metals, no electrons came off at all, regardless of intensity, regardless of how long you waited. This last part was the strangest part. If light were a wave continuously delivering energy to the surface, you would expect that enough time under even dim light would eventually accumulate enough energy to free an electron, slowly, like water wearing down stone. But that did not happen. Below the threshold frequency, nothing. Not slow release, not delayed release. Nothing. Einstein's packet explanation made all of this immediate. A packet of light carries an energy equal to Planck's constant multiplied by the frequency. That is its energy. All of it. It delivers that energy all at once, to a single electron in a single interaction. The interaction either has enough energy to free the electron from the metal, in which case it does immediately, or it does not, in which case nothing happens. Intensity means more packets per second, so more electrons freed per second, but each interaction is still one packet to one electron, and the energy per packet does not change with intensity. Below the threshold frequency, each packet simply does not carry enough energy. No accumulation is possible because there is no accumulation. There is only the packet, arriving whole, either enough or not. The explanation took half a page. The strange thing is that Einstein was not entirely comfortable with it either. He knew what he was proposing. He knew that Young's double-slit experiment had established the wave nature of light beyond any reasonable doubt, and he knew that his proposal, that light came in discrete packets, that those packets behaved in some ways like particles, was in direct tension with that. He did not resolve the tension. He named it clearly in the paper, and then he offered his heuristic and moved on. The word heuristic was doing real work. He was not saying the tension was resolved. He was saying, set the tension aside for a moment and look at what this assumption explains. What it explained was everything that was wrong with the photoelectric effect. The Nobel Committee gave him the prize for it in 1921, not for relativity, for this, which surprised some people at the time and surprises some people still. But the committee was not wrong. The photoelectric effect was the first place where the quantum picture moved from an equation fitting trick to a physical claim about how light actually behaves, and that movement was one of the most consequential steps in the history of physics. 16 years passed between the paper and the prize. 16 years during which the claim was tested and confirmed and extended and argued about. Robert Millikan, an American physicist who did not believe Einstein's interpretation, spent 10 years building increasingly precise experiments to disprove it, and every experiment confirmed it. He eventually accepted the result and won his own Nobel Prize, partly for the measurements that had been intended to show Einstein was wrong. This happens in science more than you might think. The experiment designed to close a door discovers that the door is exactly as open as the other person said it was. What changed in those 16 years was not just the status of the photoelectric effect. It was the status of the question it raised. If light comes in packets that behave like particles, and light also produces interference patterns that only waves can produce, then what is light? This question was asked by very serious people in very measured language, and none of the answers were satisfying, and the unsatisfying answers were not a temporary condition waiting to be resolved by the next experiment. They were, as it turned out, the permanent condition. The question does not resolve. It opens. because the answer is not that light is a particle and not a wave, or a wave and not a particle, or something with features of both, or something that changes depending on how you look at it. The answer is that particle and wave are categories from your scale, and at the scale of light, those categories bend. The thing that light is does not fit into either of them. It fits into the mathematics, precisely, reproducibly, without error. But the mathematics does not produce a picture you can hold in your head and feel satisfied by. Einstein knew this. He spent decades trying to find a more complete picture, one where light would have some underlying continuous nature that explained both the interference and the photoelectric effect without contradiction. He did not find it. As far as anyone has been able to determine in the 100+ years since, it is not there to be found. Light is what it is. The mathematics describes it. The description works. The picture of what it is, underneath the mathematics, is the picture we are still sitting with, still slightly uncertain about, still finding ways to phrase differently in hopes that a different phrasing will feel like an answer. Your retina catches the packets. Your brain calls it light. And somewhere underneath that ordinary event, the thing that arrived at your eye was neither wave nor particle, and both at once, and the room went from dark to bright, and you adjusted. The electron does not travel. There is no path here. This is the first thing to know, not a hidden path, not a path too small to see. The absence is not a measurement problem. Between here and there, for an electron, the path does not exist in any form that physics recognizes. The question of where the electron was at some point during its transit is not a question with an answer waiting in a drawer somewhere. The drawer is not there. Start small. An electron leaves a source. An electron arrives at a detector. Both events are real. Both can be measured. The arrival registers. The departure can be verified. These endpoints are solid ground, the kind of factual bedrock that physics is comfortable standing on. Between them is nothing that deserves to be called a journey. This is not poetry. It is not a philosophical position that some physicists hold and others dispute. It is the content of the mathematics that has described electrons with extraordinary precision for nearly a century, tested in more ways than can be easily counted, and not once found wrong. The electron, between measurements, is described by a wave function. The wave function is a mathematical object that extends through space, assigns a probability amplitude to every location, and evolves according to Schrödinger's equation in a smooth and deterministic way. It does not say the electron is here. It does not say the electron is there. It says the electron has a certain amplitude at every point in space, and that amplitude is related to how likely you are to find the electron at that point if you look. If you look. Those two words carry almost everything. The wave function spreads. It goes everywhere its equation allows, simultaneously without preference. Around a corner, through a gap, along two routes at once. It is not that the electron goes one way and you do not know which. The wave function travels both ways. The thing the wave function describes is not a particle taking an unknown path. It is something taking all paths, weighted by their probability amplitudes, and the paths interfere with each other the way waves interfere. This is why the interference pattern appears in the double-slit experiment. Not because the electron somehow goes through both slits. Because the thing the electron is, before measurement, is spread across both slits, and the two parts of the wave function meet on the other side and interfere, and the interference pattern is where the probabilities add up and where they cancel. And if you put a detector at one of the slits to find out which slit the electron went through, the interference pattern disappears, not because the detector disturbed the electron physically, because the act of finding out which path collapsed the wave function to one path, and one path does not interfere with itself. Sit with that for a moment. The information changed the outcome, not the detector, not the physical interaction, but the information, the knowing. The difference between a setup where you can find out which path and one where you cannot is the difference between a particle and an interference pattern. The universe at this scale seems to know what the experimental setup is capable of revealing. That sentence feels wrong. It should feel wrong. It is not how we expect the universe to work. We expect the universe to do what it does regardless of whether anyone is watching or measuring or knowing. The electron is somewhere, and the fact that we do not know where it is should not affect where it is. But the interference pattern disagrees. Richard Feynman, who understood quantum mechanics as well as anyone has, said that the double-slit experiment contains the heart of the mystery of quantum mechanics, that if you really understood what was happening at that slit, you would understand everything. He also said, and he said this carefully, not as a provocation, that nobody understands quantum mechanics. He did not mean that physicists could not use it, could not predict with it, could not build things with it. He meant that the understanding you develop in other areas of physics, the feeling of comprehending what is happening, of having a picture in your head that corresponds to the reality, that feeling does not arrive in quantum mechanics. Something else arrives. You get the math. The math works. The picture is missing. The electron does not travel. It has no path. And the non-path it does not take is the thing that produces the pattern on the screen. And the pattern on the screen is one of the best confirmed experimental results in all of physics. Something went from the source to the detector. Something produced the pattern. And whatever that something was, it was not a particle travelling a path, and it was not a wave in any medium, and it was not a thing we have a good name for in the language we use to describe things at the scale we live. The thread, followed to its end, comes here. The electron does not travel. The path does not exist. The measurement creates the fact of the position, and before the measurement the position is genuinely not a fact, not unknown, not hidden, not there. And yet here we are, made of electrons, and the chair beneath you is made of electrons, and the solidity of that chair is a consequence of the quantum mechanical behavior of those electrons, the Pauli exclusion principle, preventing them from occupying the same state, the electromagnetic repulsion arising from wave-like probability distributions, the whole hard fact of the physical world emerging from a substrate that, at its own scale, does not have hard facts about where it is. The chair is solid. The electrons it is made of do not have positions between measurements. Both of these things are true at the same time. That is where the thread goes. Interference. The pattern is already on the screen. You did not see it build. You were not there when it started accumulating, when the first electron arrived and left its small mark, when the second arrived, and the third, each one landing in a spot that looked random, each one adding to a distribution that was slowly, over many arrivals, beginning to show its shape. By the time you're looking at it, the pattern is clear. Bright bands and dark bands alternating, spaced with a regularity that has a mathematical structure you could calculate in advance if you knew the wavelength of the electrons and the distance between the slits. You could calculate it in advance. That is the part that is worth dwelling on. The calculation uses the wavelength, not the mass of the electron, not the charge of the electron, but the wavelength, a property that classical physics does not assign to particles at all, a property that belongs to waves, that refers to the distance over which a wave repeats itself, that makes no obvious sense as a description of a thing you can isolate and detect as a single point. And yet, the equation works. The predicted spacing of the bands matches the observed spacing, not approximately, exactly. Within the precision of the measurement, you put numbers in and numbers come out, and the numbers are correct, and the correctness is not luck because it happens every time, with every setup, and every variation, and every electron and every particle that behaves this way, which turns out to be all of them. Here is the question that orbits this experiment and never quite lands. What is interfering? Interference is something two waves do when they meet. Water waves, sound waves, light waves. When they occupy the same space, their amplitudes add. Where they add constructively, the combined wave is larger. Where they add destructively, they cancel. The pattern of addition and cancellation, projected onto a surface, produces the bright and dark bands. For two water waves to interfere, you need two water waves. For two sound waves to interfere, you need two sound waves. For the electron to produce an interference pattern, you need, and here is the problem, you need the electron to interfere with itself, because the electron is sent through one at a time. One electron, then a pause, then another. The electrons arrive individually, one after another, and no electron is in the apparatus at the same time as any other electron. And the pattern still builds. The implication is quiet, but it does not go away. Each individual electron somehow contributes to a pattern that requires interference. Each single electron lands at a position that seems random, but the distribution of those random positions, accumulated over many electrons, forms the interference pattern, which means each electron must have, in some sense, gone through both slits, must have occupied both possible paths, must have interfered with its own possible selves, weighted the paths by their probability amplitudes, and then resolved, upon hitting the detector, to a single point. This is the description quantum mechanics gives. The wave function of the electron goes through both slits. The two parts of the wave function meet on the other side. They interfere. The result is a probability distribution that looks like an interference pattern. When the electron is detected, the wave function collapses to a point, and that point is drawn from the probability distribution. The description is complete. The description works. The description does not explain what is actually happening, because what is actually happening is the description, and if you want something under the description, you are asking for something quantum mechanics does not contain. In 1961, Klaus Jonsson performed the experiment with electrons so precisely that the individual bands could be clearly resolved and measured. In 1974, Pier Giorgio Merli and colleagues in Bologna did it with electrons sent one at a time, and captured on film, frame by frame, electron by electron, showing the pattern accumulate from what looked like random noise into clear fringes, In 1989, a team in Japan repeated it with improved equipment, slower rates, higher resolution, the same result. In 2002, the journal Physics World asked its readers to vote for the most beautiful experiment in physics. The double-slit experiment with electrons won. Beautiful is not quite the word. It is something more uncomfortable than beautiful. It is a thing that produces a precise result through a mechanism that cannot be fully visualized. And the precision and the unvisualizability are connected. They are both features of the same underlying structure, and the combination of high precision with low picturability is something human aesthetic sense was not designed to process. So it comes out feeling like beauty, when maybe what it is something more like vertigo. What happens when you close one slit? The interference pattern disappears. Of course it does. With only one path available, the wave function goes through one slit, spreads on the other side in a single slit diffraction pattern. Still a wave pattern, still spread out, but not the two-source interference pattern, and the bands collapse into a single broad distribution centered on the slit. This seems obvious, and it is. And it also quietly confirms the whole picture, because if the electron were simply going through one slit or the other without knowing about the other slit, then which slit you close should not matter for the electrons that went through the open slit. They went through that slit. They did not interact with the other slit. Why should closing the other slit change their pattern? Because they did not go through just one slit. The wave function went through both. The wave function is not the electron in the sense of a particle travelling. It is the electron in the sense of the full quantum description of the electron state, and that description included both paths, and when you remove one path you change the description, and the description is what produces the pattern. The orbit continues. The same idea, approached from one more angle. If you set up a detector to catch which slit each electron goes through, a which-way detector, physicists call it, which is a charmingly direct name, the interference pattern disappears, not gradually, immediately. As soon as the experimental setup is capable of telling you which slit, the fringes go, even if you never actually look at the detector's output, even if the detector is there but you decide not to check it. As long as the information is encoded somewhere in the physical world, is in principle accessible, the pattern goes. This last part, the in principle, is the part that most people understandably do not accept on first hearing. Surely it should matter whether you actually look. Surely the electron does not know whether you intend to check the detector, but the experiments confirm it. The pattern responds to the presence of information in the environment, not to the act of a human looking. The information encoded in the detector, regardless of whether anyone reads it, is enough. And this turns out to be connected to something called decoherence, the process by which quantum systems entangle with their environments and lose their wave-like behavior. But that comes later. For now, the pattern, the fringes, the fact that each electron alone in the apparatus produces a pattern that only interference can explain. The orbit keeps going. The explanation keeps working. The thing in the center of the orbit, what the electron actually is, what the wave function actually is, what it means for a probability amplitude to go through a slit, stays where it is, unresolved, producing interference. The screen is still lit, the pattern is still there. Whatever made it go that way was not a particle taking a path. and whatever made it collapse to a point when you looked was not a particle that was always going to land there. And the pattern and the point are both real and both produced by the same electron, and the description that contains both is exactly right and also completely resistant to being pictured. The fringes, still there. 5 men in a room who disagreed about what they had found. The argument was already over by the time most people heard about it, or it seemed over. The mathematics had converged, the predictions were working, the theory was producing numbers that matched experiments better than anything physics had produced before, and the people who had built the theory were beginning, in their different ways, with their different temperaments, from their different starting positions, to try to say what it meant. This is where the trouble was. Building a theory and saying what it means are different activities. Building requires mathematical consistency and experimental confirmation. Saying what it means requires something else, something more like philosophy, or perhaps something that does not have a good name yet. A kind of disciplined staring at the structure of what you have made until the structure says something back. The structure was saying something. The people staring at it were not all hearing the same thing. Niels Bohr, by the mid-1920s, had been living with quantum strangeness longer than almost anyone. He had built the 1913 model of the hydrogen atom, watched it succeed and fail in specific ways, participated in the decade of work that replaced it with something more complete and more strange. He had thought carefully and at length about what it meant to ask questions about a quantum system. His answer, developed with Werner Heisenberg and others in Copenhagen, and known as the Copenhagen interpretation, was that the question of what a quantum system is doing between measurements is not a question physics can answer, and, more strongly, that it is not a question that has an answer. The wave function is not a description of a real thing in the world. It is a calculation tool, a way of predicting outcomes. To ask what the electron is really doing when nobody is measuring it is to ask something outside the scope of what physics is for. Bohr did not say this flippantly. He came to it slowly, through sustained engagement with the experimental results and the mathematical structure, and he defended it with a precision and a patience that made it hard to dismiss, even for people who found it deeply unsatisfying. Einstein found it deeply unsatisfying. He found it unsatisfying in a way that lasted for the rest of his life. The disagreement between Bohr and Einstein is one of the most thoroughly documented scientific arguments in history. They met repeatedly over decades, at conferences and in correspondence, and the argument had a quality of genuine mutual respect combined with fundamental irreconcilability that makes it unusual in the history of disputes. Einstein was not hostile to quantum mechanics in the way that a crank is hostile to an established theory. He knew the theory worked. He had contributed to it. He accepted its predictions. He simply believed that it was incomplete, that there was a deeper level of description, a set of hidden variables, a more complete account of reality that would explain the quantum results without the irreducible randomness and without the dependence on measurement. He did not believe God played dice. He said this more or less in various forms more than once. Bohr apparently replied, also more than once, that Einstein should stop telling God what to do. The argument was not resolved in either of their lifetimes. In one precise technical sense, it was not resolved until 1964, 9 years after Einstein died, when John Bell published a theorem showing that no hidden variable theory of a certain class, local, meaning that influences cannot travel faster than light, could reproduce all the predictions of quantum mechanics. And the subsequent experiments confirmed quantum mechanics and ruled out local hidden variables. Einstein's hope, in its specific form, was not available. This did not settle the question of what quantum mechanics means. It settled one of the options. The others remain. Werner Heisenberg had arrived at quantum mechanics through a different path than Bohr. Where Bohr had started from the atom and worked outward, Heisenberg had started from the mathematics and worked inward. In 1925, during a period of hay fever recovery on the island of Helgoland, he had developed the first complete formulation of quantum mechanics, matrix mechanics, in a form that deliberately avoided referring to any unobservable quantities. Positions and velocities of electrons between measurements, not in the formalism, only what could be measured, what showed up in the data, what had an experimental correlate. The theory was built to match the observables and not make claims about anything else. Heisenberg's uncertainty principle, which he published in 1927, came from this. It is usually presented as a statement about measurement disturbing systems. You have to shine light on an electron to see it, and the light kicks it, and the kick disturbs its momentum. But this is not quite what it says. What it says is more fundamental. The position and momentum of a quantum system are not simultaneously defined, not simultaneously unknown, not simultaneously hidden, simultaneously not there. The more precisely one is defined, the less precisely the other can be defined, not because of measurement disturbance, but because of the structure of the wave function itself. Position and momentum are incompatible descriptions. You can have one or the other to varying degrees, but the product of their uncertainties has a lower limit, and the lower limit is Planck's constant divided by 2. This is a statement about nature, not about instruments. Erwin Schrödinger built his wave equation in 1926 and almost immediately disliked what it implied. He had hoped the wave mechanics would restore something continuous and intuitive to physics. He thought the wave function might be a real physical wave, a density distribution of the electrons smeared through space, and that the quantum jumping and discreteness of Bohr's model were artifacts that a cleaner wave picture would dissolve. Max Born, shortly after, showed that this interpretation did not work. The wave function squared gives a probability density, not a charge density, and probabilities are not physical things in space the way charge densities are. And Schrödinger found this genuinely distressing. He invented the cat to express the distress, not to propose that cats could be in superpositions, to show that if you took the Copenhagen interpretation seriously, you ended up with a situation where a cat was neither alive nor dead until you looked at it, which he found absurd, and he offered it as a reductio ad absurdum, as a demonstration that something was wrong with the interpretation, not that the interpretation was right. The cat became famous for the wrong reason. Louis de Broglie had proposed in 1924 that particles had wavelengths. In 1927, he went further and proposed the pilot wave theory. A real particle, with a definite position at all times, guided by a real wave that surfs through the environment and sets up interference patterns. The particle always has a position. The randomness comes from our ignorance of the initial conditions. The wave is real and physical and deterministic. The theory reproduced all the predictions of quantum mechanics for single particles. It was ignored by almost everyone for 30 years. David Bohm rediscovered and extended it in 1952. It is still a minority position, still mathematically consistent with all known experiments for non-relativistic systems, and still not widely adopted for reasons that are partly aesthetic and partly practical, and partly the accumulated weight of a community that had decided on something else. 5 men, 5 positions, one set of mathematical results, pointing in the same direction, interpreted in ways that did not agree about what a physical system was, what a measurement did, whether randomness was fundamental or epistemic, whether the wave function was real or a calculation tool. The sediment that settled from this period was not a consensus on meaning, it was a consensus on method. Physicists adopted a working stance sometimes called shut up and calculate. Do the math, predict the outcome, compare to experiment, repeat. Questions about what the wave function is, whether the electron has a position between measurements, what happens during a measurement, these were bracketed, set aside, not answered, not dismissed, just placed outside the scope of daily practice. This worked. The physics advanced, the transistor was built, the laser was built, quantum field theory was developed and confirmed with extraordinary precision. The practical program succeeded on terms that classical physics had never managed. The argument about meaning did not disappear. It went underground into the philosophy of physics, where it is still being had, in careful and technical language, by people who take it seriously and know it matters. None of the 5 men were entirely right. None were entirely wrong. The math they built is still the math. The argument underneath it is still open. The cat was never the point. You already know about the cat. Almost everyone does. It has appeared in physics textbooks and philosophy papers and television shows and casual conversations and coffee mugs and t-shirts and at least one very bad pop song. The image of a cat that is both alive and dead, sealed in a box, suspended between 2 states until someone opens the lid and looks. This image has become the unofficial mascot of quantum weirdness, the thing people reach for when they want to gesture at how strange it all is. Schrödinger was irritated. He put the cat there as an irritation, and what it became instead was a brand. The thought experiment, published in 1935, was a response to something specific. Bohr and the Copenhagen interpretation had said, in various formulations, that quantum systems exist in superpositions of states until measured, at which point the wave function collapses to a definite outcome. For a single electron, this is hard to argue with experientially, because electrons are not things you can see in your ordinary life, and the weirdness stays safely at a scale that does not disturb you. Schrödinger wanted to disturb you. He proposed a setup in which a quantum event, the decay or non-decay of a radioactive atom over the course of an hour, was linked via a detector and a relay mechanism to a vial of poison inside a sealed box containing a cat. If the atom decays, the detector triggers, the relay breaks the vial, the cat dies. If the atom does not decay, nothing happens, the cat lives. After an hour, without opening the box, you do not know which outcome occurred. According to the Copenhagen interpretation, the atom is in a superposition of decayed and not decayed until measured. The superposition presumably propagates through the detector and the relay to the poison vial to the cat. The cat, therefore, is in a superposition of alive and dead. Schrödinger found this conclusion unacceptable. He was not proposing that cats can be in superpositions. He was proposing that a framework that implies this about cats must be missing something. The reason the thought experiment got away from him is that it is genuinely vivid. A cat is not an electron. A cat is something you can picture. A cat in a superposition is an image the mind can hold if uncomfortably, and hold makes it feel real in a way that the electron in a superposition does not. The weirdness becomes touchable, domestic. You can imagine the box. You can almost hear the silence inside it. What you cannot do, quite, is decide what to do with the image, and that, the not knowing what to do with it, is exactly what Schrödinger intended. Not as a cute puzzle with a solution on the back page, as a genuine challenge to the interpretation. He was saying, your framework produces this. Is this acceptable? The Copenhagen response, roughly, was yes. A macroscopic system like a cat becomes entangled with its environment so rapidly and so extensively, interacting with air molecules, photons, thermal fluctuations, that its quantum coherence is lost almost instantly. The superposition of alive and dead does not persist in any meaningful sense, because decoherence destroys it before it can develop into anything you could measure. The cat is not in a superposition in practice. The isolation required for quantum coherence at macroscopic scales is not achievable. This is correct. It is also not quite the point Schrödinger was making. He was making a logical point about the structure of the interpretation, not a practical point about whether you could build the box. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the cat seriously in a different way. In Everett's picture, the wave function never collapses. Instead, it branches. When the atom either decays or does not, the universe divides into two branches, one in which it decayed and the cat is dead, one in which it did not, and the cat is alive. Both branches are real. The observer in each branch sees a definite outcome. Neither branch knows about the other. The randomness of quantum mechanics becomes the indexing of which branch you happen to be in. This interpretation is mathematically clean. It avoids the need for a collapse mechanism, which has always been a weakness in interpretations that require one, because the Schrödinger equation is deterministic and linear, and collapse is neither. It also implies an enormous, probably infinite proliferation of parallel universes, each one as real as this one, each one containing versions of you and the cat and the radioactive atom in every possible configuration. I find myself genuinely uncertain, not as a rhetorical move but as an honest position, about which of these pictures is right. I do not know if any of them is right in the way I mean when I use the word right. The math is the math. The interpretations are frameworks for deciding what the math is describing, and the frameworks are not testable against each other by any experiment currently known, which is a strange place to be after a century of doing extraordinarily precise experiments. The cat is not alive and dead. The cat is, or rather, the situation described by the thought experiment is, a picture of the measurement problem wearing a fur coat. The measurement problem is the question of how a quantum system, described before measurement by a wave function spread over multiple possible outcomes, produces a single definite outcome when measured. Where does the other possibility go? What happens to the part of the wave function corresponding to the outcome that did not occur? The Schrödinger equation has no mechanism for this. The equation evolves the wave function smoothly and deterministically. Collapse is something added on top of the equation by hand as a rule for when the equation stops applying. This bothers physicists who want their fundamental equations to be fundamental all the way down. The cat makes this visceral. That is what it was for. It was not for coffee mugs. Something worth asking yourself, if you're in the mood. Does the interpretation matter? If all the interpretations make the same experimental predictions, does it matter which one is true, or whether any of them is true in a deep sense? Some physicists say no. The predictions are what matter. The pictures are aids to intuition, and when the intuition fails at this scale, the pictures become liabilities rather than assets, and you are better off without them. Other physicists say yes, absolutely, because the picture shapes what questions you think to ask, which shapes what experiments you design, which shapes what you discover, and a wrong picture can close off an entire direction of inquiry by making certain questions feel already answered. I do not know who is right. Both positions have been defended by people whose thinking I respect, and I have sat with both for long enough to see the force in each. The cat sits in the box is still closed, not because nobody has opened it, but because opening it is a harder problem than it looks, and the opening requires not just an experiment but a framework for deciding what seeing the result would mean. And the framework is the thing we do not agree on. Probability all the way down. There is a game that children play where they flip a coin and guess, and the important thing about the game, the thing that makes it a game at all, is that the answer is hidden. The coin is in the air, or under a palm, or not yet flipped, and the not yet knowing is the gap the game lives in. And when the answer is revealed, the game ends, and a new one begins. Probability, in this game, is a measure of ignorance. You say 50-50 because you do not know. And if you did know, you would say certain or impossible, and probability would disappear entirely. This is how probability worked in physics before quantum mechanics. Classical probability was always a placeholder for missing information. Given complete knowledge of a system's initial conditions and the forces acting on it, classical mechanics was deterministic. The coin flips the way it flips because of specific angles and forces and spin rates, and if you knew all of those perfectly, you could predict the outcome perfectly. Probability was the word for what you said when the knowledge was not available. It was a feature of the map, not the territory. Quantum mechanics changed this, and the change was not a small one, and it took a long time for the change to be clearly articulated. Max Born in 1926 wrote a short paper proposing that the wave function squared gives the probability density for finding a particle at a particular location. He later said he almost did not include this interpretation, that he added it almost as an afterthought in a footnote. The footnote turned out to be one of the most consequential statements in 20th century physics. It won him the Nobel Prize in 1954. What Born's rule said, in its implications, was that the probability in the wave function was not a placeholder. It was not ignorance. The electron did not have a definite position that you simply did not know. The electron had a wave function, and the wave function squared told you the probability distribution, and before measurement there was no position, and the probability was all there was. Not all there was of your knowledge, all there was of the electron's position in nature, full stop. This is the step that Einstein could not take, not because he was behind the times or stubborn or had missed something, because it requires accepting that the universe is, at a fundamental level, irreducibly random, that the outcome of a quantum measurement is not determined by any prior state of the system, that there is no fact about the universe that, if you knew it, would tell you which outcome will occur. The outcome is genuinely open until it happens. Einstein wrote about this to Bohr in a letter and said, famously, in a way that has been translated and quoted so many times that the original German has become almost secondary, that he could not believe that God plays dice with the universe. He meant it as a statement about his intuition of how deep physical laws should work. He believed that a complete theory of nature would be deterministic, that the randomness in quantum mechanics was the signature of an incomplete description, the way fog is the signature of not being close enough to see the individual water droplets. Bohr wrote back gently and said that he was happy with the dice, that the randomness was not a temporary condition, that it was the ground. The two positions are not in the end just about taste. If Einstein were right, if quantum probability were epistemic, a matter of knowledge rather than nature, then hidden variable theories should be possible. Theories with additional information, additional variables not captured in the wave function, that would determine the outcomes that quantum mechanics could only give probabilities for. Einstein believed such theories must exist. He spent years looking for them, collaborating with Rosen and Podolsky to develop thought experiments designed to show that quantum mechanics was incomplete. Bell's theorem in 1964 showed that hidden variable theories of a specific type, local ones, meaning that the hidden variables at one location cannot be influenced by events at a distant location faster than light, cannot reproduce all the predictions of quantum mechanics. The predictions in question involve pairs of entangled particles, and the correlations between measurements on those particles and the specific degree of those correlations. Local hidden variable theories predict a limit on how strong those correlations can be. Quantum mechanics predict they can be stronger. The experiments, Clauser and Friedman in 1972, Aspect and colleagues in 1982, Zeilinger and colleagues in many subsequent experiments with progressively closed loopholes, confirmed quantum mechanics. The correlations exceed the limit. Local hidden variables are ruled out. The randomness is not just a feature of the map. So what does it mean for randomness to be fundamental? It means that the decay of a radioactive nucleus, the specific moment at which a specific nucleus emits a particle, is not determined by any prior state of that nucleus, not by its internal structure, not by its history, not by any fact about the universe that, in principle, you could have access to. The nucleus is in a state that has a certain probability of decaying per unit time, and within that probability the when is genuinely open. Not hidden. Open. It means that if the universe were run again, from exactly the same initial conditions, with the same laws, the same particles, the same fields, exactly the same in every way that physics can specify, the quantum mechanical events within it would not necessarily unfold the same way. The same probabilities, yes. The same average behavior, yes. But the specific events, the specific moments, the specific which outcomes, those could differ. The universe has a stochastic element at its core, and the stochastic element does not go away at any level of description. This makes certain kinds of determinism impossible, not in practice, but in principle. The pulse goes outward here. Classical determinism was the picture of a universe as a machine, its future already contained in its present, every later state the necessary consequence of every earlier state, the whole thing unfolding like a calculation being performed. Laplace's demon, a hypothetical intelligence with complete knowledge of all positions and momenta, could, in this picture, predict the future with perfect accuracy and retrodict the past with the same precision. The universe was its own complete description, carrying its future inside itself. Quantum mechanics removes Laplace's demon, not by hiding information from it, by establishing that the information Laplace's demon would need, the definite positions and momenta of all particles, does not exist. The demon is not being denied access. The thing it was going to access is not there. The pulse contracts. What remains is probability, not as a limitation, as the actual nature of unresolved quantum states. The probabilities evolve deterministically. The Schrödinger equation is deterministic. The wave function evolves without randomness until measurement. But the outcomes of measurements are drawn from probability distributions, and the drawing is irreducibly random, and no extension of the theory is known to remove this. The pulse goes outward again. If randomness is fundamental, then novelty is possible in a way it would not be in a fully deterministic universe. If the future is not already contained in the present, then there is room in the universe for things to happen that were not, in any meaningful sense, already going to happen. This does not resolve the questions of free will or causality or moral responsibility that humans care about. It moves them. It places them in a universe where the bottom is not fixed. The pulse contracts again. The probability, the wave function, the number between 0 and 1 that tells you how likely, and the event that then either happens or does not, and the after-the-fact definiteness of the result that carries no memory of the probability it came from. The coin was never in the air. The coin did not exist until it landed, the places it went that nobody expected. The transistor was invented in 1947. The three men who made it, John Bardeen, Walter Brattain, and William Shockley, were not trying to demonstrate quantum mechanics. They were trying to build a better amplifier. What they built was the device that now sits inside every piece of electronics you own, in quantities that are difficult to state without the number becoming meaningless. Modern microprocessor chips contain tens of billions of transistors. The manufacturing processes that make them work operate at scales where quantum effects are not incidental but load-bearing. The transistor works because of the quantum mechanical behavior of electrons in semiconductor crystals. The energy band structure of silicon, the allowed and forbidden energy levels for electrons moving through the crystal lattice, is a direct consequence of the quantum mechanics of electrons in a periodic potential. The gap between the valence band and the conduction band, the thing that makes silicon a semiconductor rather than a conductor or an insulator, is a quantum mechanical fact. It is there because of the wave nature of electrons interacting with the crystal structure, the interference of those waves with the lattice, the resulting forbidden energies. Take away quantum mechanics, and you do not get a worse transistor. You do not get a transistor at all. The laser followed in 1960. Theodore Maiman built the first working one using a synthetic ruby crystal and a flash lamp, and the output was a pulse of coherent red light that the lab photographed, and then apparently not everyone immediately understood the significance of. The laser depends on stimulated emission, a process Einstein had predicted in 1917, where a photon encountering an excited atom can trigger that atom to emit a second photon that is identical in frequency, phase, and direction to the first. This only works because of quantized energy levels. The atom has discrete states. The photon has an energy matching the gap between them. The interaction is coherent in a way that only quantum systems can be. The coherence of laser light, the thing that makes it different from ordinary light, the thing that makes it useful for cutting steel and reading discs and measuring distances and performing eye surgery and lately doing an enormous range of other things. That coherence is a quantum effect. The sun produces energy through nuclear fusion. 4 hydrogen nuclei fuse through a chain of reactions into a helium nucleus, and the mass difference appears as energy. This process requires the nuclei to get close enough for the strong nuclear force to take over. But the nuclei are positively charged and electrically repel each other, and the temperature at the core of the sun, though extraordinarily high, around 15 million degrees Kelvin, is not high enough, classically, for the nuclei to overcome this repulsion. The kinetic energies are too low, the barrier is too high. Classically, the fusion should not happen at the rate it does. It happens because of quantum tunneling. The protons do not need to have enough energy to go over the barrier. They tunnel through it. The wave function of a particle approaching a potential barrier extends into the barrier and emerges on the other side with a non-zero amplitude, meaning there is a non-zero probability that the particle will be found on the other side even without enough energy to get over the top. The probability drops exponentially with the width and height of the barrier and the mass of the particle, so tunneling is negligible for macroscopic objects, but significant at nuclear scales. For the proton-proton fusion in the Sun, tunneling enhances the reaction rate by a factor of many orders of magnitude compared to what the classical calculation would give. The Sun shines because particles can go places they classically should not be able to reach. This has been happening for 4.5 billion years. Your warmth at this moment comes from quantum tunneling. Tunneling also underlies the mechanism of certain chemical reactions. Hydrogen atoms are light enough, and the barriers involved in some reactions small enough, that tunneling contributes meaningfully to the reaction rate, even at room temperature, even in biological systems. Enzyme catalysis, in at least some cases, appears to involve proton or hydrogen tunneling that accelerates reactions far beyond what thermal activation alone could achieve. The field is active and not fully resolved, but the contribution of quantum tunneling to biochemical processes is no longer a speculative claim. The sense of smell is more complicated than it appears. You have olfactory receptors in your nose that bind to specific molecules and trigger signals that your brain interprets as smell. The classical picture is lock and key. The shape of the molecule fits the shape of the receptor, and the fit triggers the signal. The picture is largely correct. But some evidence suggests that the vibrational frequencies of molecules also play a role in odor discrimination, that receptors are sensitive not just to molecular shape, but to the specific quantum mechanical vibrations of molecular bonds in a way that might involve inelastic electron tunneling within the receptor. The evidence is contested, the mechanism is not settled. But the possibility that you smell partly by quantum sensing, that what you experience as a particular scent involves your olfactory system detecting the quantum vibrational signature of a molecule, is taken seriously by a small but credible community of researchers. Your nose might be doing quantum mechanics. The jury is still out on exactly how. European robins navigate during migration using what appears to be a quantum compass. The evidence, built up over years of careful experiment by Henrik Moritzen, Thorsten Ritz and others, points to a mechanism in which cryptochrome proteins in the bird's eye, when activated by light, produce pairs of electrons in a quantum entangled state called a radical pair. The orientations of these paired electrons relative to the Earth's magnetic field evolve in a quantum mechanically sensitive way, and the outcomes influence chemical reaction rates in the protein, which the bird's nervous system detects as directional information. The bird navigates by the magnetic field partly because of quantum entanglement, maintained in a warm, wet biological system for microseconds at a time, long enough to be useful. Quantum coherence in biology was considered unlikely for a long time, on the grounds that warm, wet environments would destroy it too quickly. The radical pair mechanism in cryptochrome appears to be an exception. There may be others. What these things share is not a theme. They are not arranged here to make a point. They accumulated one at a time as physicists and chemists and biologists and engineers pressed the quantum formalism into new areas and found it there waiting, already correct, already describing something that had been working without being understood. The quantum behavior of electrons in crystals was there before anyone built a transistor. The stimulated emission that makes lasers work was there before Einstein predicted it. The tunneling that fuels the sun was there before Gamow calculated it in 1928. The radical pair mechanism was operating in the robin's eye before anyone suggested it. None of these things required quantum mechanics to exist. They required it to be understood. And the strange thing, the thing that settles last, because it is the most counterintuitive, is that quantum mechanics did not arrive at the world from outside and change it. It arrived at the world and described what was already happening. The grain was there. The discreteness was there. The tunneling was there. The entanglement was there. It had always been there, underneath everything, doing what it does. Nothing is touching and everything is correlated. Two particles are prepared together in a specific way. That is all. That is the beginning of the thing. Two particles, produced in the same event, sharing a common origin, going off in opposite directions. Everything that happens after is a consequence of that beginning. The particles move apart. The distance between them grows. They pass through apparatus and fields and they travel. And if you wait long enough, the distance between them is whatever distance you want it to be. Kilometers. In experiments that have been done, the distance has been hundreds of kilometers. The particles have not been in contact since the moment they were produced. There is nothing connecting them in any way that classical physics would recognize. They are just two particles, far apart, going about whatever particles do when nobody is measuring them. Then someone measures one of them. What happens when you measure a quantum system is that the measurement selects an outcome from the probability distribution the wave function describes, and the wave function, for that system from that point reflects the outcome that occurred. The other possibilities are gone in the practical sense that they no longer contribute to subsequent predictions for this system. This is wave function collapse in the operational language, and whatever it means at a deeper level is the subject of the interpretation debates we have already been through. For a single particle, this is strange but manageable. The weirdness stays local. For two particles that were produced together in a specific quantum state, an entangled state in the language of the formalism, the measurement on one of them affects the description of the other immediately, regardless of how far apart they are. The specific case that has been studied most extensively involves spin. Particles like electrons have a quantum property called spin, which behaves like angular momentum in some ways and defies the classical concept of rotation in other ways. It is better to think of it as a quantum mechanical property that has measurable values and follows specific rules than to think of a little ball spinning, because the little ball model goes wrong quickly. Spin in a given direction can be measured to be either up or down. If you prepare two electrons in an entangled state where their total spin is zero, then if one electron is measured spin up in a given direction, the other electron is necessarily spin down in that same direction when measured. This would not be surprising if the spins had been set at the moment of preparation. If the first electron had always been going to be spin up, and the second had always been going to be spin down, and the measurement simply revealed the pre-existing fact, this is the hidden variable intuition, the intuition that Einstein's EPR argument was pushing toward. The correlations are real, but they are classical correlations, like gloves in separate boxes. Opening one box and seeing a left glove tells you the other box contains a right glove without any spooky influence at a distance. Bell's theorem showed that the quantum correlations are stronger than any such classical explanation allows. The theorem works by considering measurements made in different directions, not just up-down but various angles. If the spins had definite values set at preparation, the correlations between measurements at different angles would be constrained by a specific inequality, Bell's inequality. Quantum mechanics predicts correlations that violate the inequality. The experiments confirm the quantum predictions. The inequality is violated. The classical hidden variable explanation is ruled out. What this means is that the correlations between the two particles cannot be explained by information each particle carries from the moment of preparation. The particles do not know in advance how they will be measured. The correlation between their outcomes is genuinely produced at the moment of measurement, and it is produced in a way that is coordinated between the two particles regardless of the distance between them. Einstein called this spooky action at a distance. The phrase has become famous. The thing it describes has been confirmed. The thread tightens here, because the confirmation raises something uncomfortable. The coordination between the particles is instantaneous, or at least faster than any signal travelling at the speed of light could account for. The correlation exists across the space-like separation. If you measure both particles simultaneously, in different locations, with no time for a light-speed signal to travel between them, the outcomes are still correlated in the way quantum mechanics predicts. This is not a loophole. It has been tested. The experiments done by Aspect in 1982 and refined by Zeilinger and others in experiments closing successive loopholes through the 1990s and 2000s culminating in loophole-free Bell tests in 2015, are about as clean as physics gets. The correlations are there. They cannot be explained by local classical mechanisms. But the correlations cannot be used to send information. This is the crucial point, and it is the point that saves the rest of physics from having to be rewritten. You cannot use entanglement to send a message. When you measure your particle, you get a random outcome, up or down, and the other particle will be correlated with that outcome, but neither you nor anyone else can control which outcome you get. The randomness prevents signaling. The correlation exists, but you cannot exploit it to transmit information faster than light. Relativistic causality is preserved. The spookiness is real. The non-locality is real. The information cannot travel. All three of these are true at the same time. What to make of this is genuinely unclear to me, in a way that feels different from the ordinary uncertainty of not having studied something enough. The two particles are separated by enough distance that no signal travelling at the speed of light could coordinate them, and yet they are coordinated. The coordination is not in a hidden variable. The coordination is in the quantum state they share, the entangled state, the mathematical object that describes them as a single system, with properties not reducible to properties of the individual particles. The quantum state of the two-particle system is a single thing, not two things that are connected. One thing that extends across the space between them and describes them jointly. When the measurement happens, it happens to the whole state, and the whole state responds, and the responses at the two locations are the correlated outcomes, and there is no mechanism in the formalism for how the response travels from one location to the other, because in the formalism there is nothing to travel. The state is not here and there, it is just the state. Whether this means non-locality is real, or that the notion of location is more complicated than it appears, or that the universe does not have a preferred way of being sliced into separate things, I do not know. Physicists whose judgment I find careful and considered hold different views on this. The mathematics does not adjudicate. The mathematics just computes the correlations correctly. Two particles far apart sharing a state that is one thing. The measurement selects an outcome. The other outcome is gone. The distance between them never mattered. The thread ends there, in something that is correct and unresolved at the same time. What it would mean to understand it. Feynman said it in a lecture. Nobody understands quantum mechanics. He said it clearly. He was not being humble. He was not performing the false modesty that occasionally appears in scientists talking to general audiences, the kind that says I cannot explain this in simple terms, when what they mean is you cannot understand it in simple terms. Feynman meant it about himself and his colleagues, about the people who used the mathematics daily, about the people who built the devices and ran the experiments and checked the numbers and got it right. Nobody understands it. What he meant needs to be unpacked carefully. He did not mean that physicists cannot use it. They can, with extraordinary precision. The anomalous magnetic moment of the electron, a tiny deviation from a classical prediction, arising from the electron's interaction with the quantum vacuum, has been calculated using quantum electrodynamics to more than 10 significant figures and measured experimentally to more than 10 significant figures, and they match. This is one of the most precise agreements between theory and experiment in all of science. Understanding in the operational sense is not in question. He meant something else. He meant the kind of understanding you have when the picture makes sense, when you can hold the thing in your head and feel its shape, when the mathematics corresponds to something you can almost see, almost touch, almost follow through with your intuition. That kind of understanding, the kind that lets you close the book and still know what the book said. That kind does not come. You can hold the Newtonian picture, masses and forces and paths through space. You can close the textbook and still see the cannonball arcing over the field and know why it does what it does. The picture and the mathematics agree, and the picture is enough to carry you through most of the reasoning without the mathematics, and the mathematics is a precise version of what the picture already told you. Quantum mechanics does not have a picture like that. The wave function is not something you can see. Its collapse is not something you can watch. The superposition is not a visible state. The uncertainty is not a visible fuzziness. The entanglement is not a visible chord. None of the entities in the mathematics correspond to anything you can construct an image of and carry around and use to check your reasoning. The mathematics is precise. The reasoning is reliable. The images are not there. Some physicists have made their peace with this more gracefully than others. David Mermin coined the phrase "shut up and calculate," which he later said was actually meant as a criticism of the attitude it described, not an endorsement of it. The attitude is, the mathematics works, the predictions match, the question of what it means is unanswerable or irrelevant, asking it is a distraction. Get back to calculating. Others have not been able to make this peace. John Bell, who proved the theorem that bears his name, spent the second half of his career arguing that the foundations of quantum mechanics were in an unsatisfactory state, and that the discomfort should not be explained away by professional norms. He wanted a clearer account. He did not get one. He died in 1990, still looking. Roger Penrose believes that the collapse of the wave function is a real physical process connected to gravity, that there is an objective threshold at which a quantum system becomes classical, and that understanding this process will require going beyond quantum mechanics into a theory that does not yet exist. His view is a minority position. It has not been ruled out experimentally. It has also not been confirmed. Lee Smolin and others have argued that the foundations crisis is a sign that quantum mechanics, for all its precision, is not the final word, that a deeper theory exists, one with a clearer ontology, and that the job of finding it is unfinished. The orbit of this chapter keeps returning to the same location, the gap between the theory's precision and the theory's picturability, because the two usually travel together. When physics knows what is happening, it knows in a way that feels like knowing. The picture and the number coexist. In quantum mechanics, they are separated. You have the number without the picture. The number is extraordinary. The absence of the picture is something you either learn to live with or you do not. I am not sure I have learned to live with it. Not fully. There is something that feels like an incompleteness when I sit with the measurement problem, the way a sentence feels incomplete when a word is missing that you cannot supply because you do not know what word belongs there. The mathematics flows. The predictions emerge. The word is still missing. What would understanding feel like if it came? Maybe it would feel like the picture arriving, like the wave function suddenly being something you could point at and say, yes, that is the thing, the electron is that. Or maybe understanding in quantum mechanics is not a picture. Maybe it is a different relationship to the uncertainty itself, a comfort with the fact that the question of what is there between measurements simply does not have an answer. And the comfort is not resignation, but is itself the understanding. Not knowing what the electron is, but knowing that the knowing what it would require does not apply here. Maybe that is what Feynman meant. Not that understanding is impossible, that the understanding available is a different shape than the understanding we were built for. The mathematics keeps computing, the experiments keep confirming, the numbers agree to 10 significant figures. The picture is still missing, and whether the missing is permanent, whether it is a feature of the territory rather than a gap in the map, is a question that a century of thinking has not closed, and that I am carrying forward without a destination in mind, and that feels, at this hour, like exactly the right question to be carrying. The measurement has already been made. The number is already written. It is in a notebook somewhere, or in the archive of a notebook, or in a photocopy of the archive, or in a paper that cited the notebook and reproduced the value. H equals 6.626 times 10 to the negative 34th joule seconds. Planck wrote it to make an equation work. He went home. He did not believe it. The lab is quiet now. The equipment from 1900 is in a museum, or dissolved, or distributed into the disorder of 120 years of entropy doing its ordinary work on physical things. The original black body radiation data that prompted the calculation exists in papers that can be read. The man who performed the calculation has been dead since 1947. The number he wrote is built into every transistor that has ever switched, every laser that has ever fired, every time a bird found magnetic north. We have moved through a century of physics in 12 chapters, and I want to stay, for a moment, in what that movement feels like from the end of it. Not to summarize. Summaries close things. This does not want to be closed, but to notice. To notice that the whole journey started with a number that its author thought was fake, and the number was real, and realizing the difference took decades, and the decades were full of careful people looking at the same evidence and arriving at different conclusions about what it meant, and none of the conclusions were final, and the ones that seemed most settled were the ones that turned out to have the most remaining open beneath them. The things from the earlier chapters look different now. Planck's constant, which in the first chapter sat quietly in a notebook, has since appeared in the energy levels of atoms, the wavelengths of matter waves, the uncertainty principle, the coherence of laser light, the tunneling that powers the sun, the radical pair mechanism in a bird's eye. It is the same number every time. It does not change. It was not placed there by Planck. It was found there by Planck in data that predated him, in a universe that had been using it since the beginning. The discreteness that troubled Planck, that felt to him like a mathematical concession, turned out to be the grain of everything, not a feature of the problem he was solving, a feature of the world the problem was describing. The flaw was always there. It is still there. Whatever you are resting on right now has a flaw beneath it that is grainy and probabilistic and described by wave functions, and does not have definite positions between measurements. This is true right now. This is true of the surface under your hands. The argument between Bohr and Einstein did not end. It reached a point where one side could be ruled out experimentally, local hidden variables, and the other side did not become right by default. What remained was the territory that interpretations occupy. Beyond what experiments can currently test, prior to what future experiments might reach, the question of what quantum mechanics means about the nature of reality is still open, and people who have spent careers on it still disagree, and the disagreement is not a failure. It is the shape of the thing. What I keep returning to, drifting through this, is the quality of the not knowing. It is not the not knowing of a problem waiting to be solved. It is not the not knowing of a gap in the data, a measurement not yet made, a calculation not yet run. It is a not knowing that appears to be structural, built into the theory at the level of what the theory says about what can be known. The wave function does not describe a hidden reality. It describes the full reality of the system, and the full reality includes irreducible probability and no definite values between measurements, and asking for more is not asking for clarity. It is asking for something the universe does not appear to offer, or the universe offers it, but the offer is in a language we have not learned to read. This is Einstein's position, still defended, still unconfirmed. The two positions look different. They feel different. They make no different experimental predictions with the tools currently available. Planck lived until 1947. He saw quantum mechanics become field theory. He saw the neutron discovered, and the fission reaction, and the beginning of the nuclear age. He saw the thing he had started become larger than anything a person starting it could have planned for. He continued, through most of his life, to believe that the quantum was an approximation of something deeper. He died before Bell's theorem. He died before the experiments. He wrote a number to make an equation work. The number was real. The measurement had already been made in the data waiting to be correctly interpreted, in the black body radiation spectrum of every hot object that had ever existed, through all the time that hot objects had been radiating, which is all of the time that has ever been. The lab is quiet, not the lab of 1900, the lab of now, wherever that is, the one doing the Bell test with photons separated by hundreds of kilometers, the one watching the interference pattern accumulate electron by electron, the one measuring the magnetic moment of the electron to 10 decimal places and finding the calculation right. These labs are not quiet, but between the results, between the numbers printed and filed and compared and confirmed, there is a quiet that is not the absence of activity, but the presence of something that does not make sound. The wave function evolves, the probabilities propagate. Nothing has been measured yet, and everything is in superposition, and the mathematics is exact, and the picture is missing, and the number is h, and it equals 6.626 times 10 to the negative 34th joule seconds, and it was there before anyone wrote it, and it will be there after, doing what it does, in every interaction at every scale, below the scale of ordinary things, which is all of the scales there are. The chapter ends, something is still going,